Hello everyone, in this video we're looking at single bodies in motion along an inclined plane. It is when an object can travel up and down an inclined plane, of course, and we are to observe the forces acting on said object. Here is an object traveling along the incline, a free body diagram. This Q represents the force driving the object forward up the hill. This line is the weight of the object relative to the horizontal plane, where gravity pulls it down. This W sine theta is the weight of the object relative to the inclined plane, where the object travels along. Here's an example from the topic note. I've changed the angle of the hill from a gradient of 1 over 30 to 30 degree for some easier calculations. Now we have a truck with a mass of 4 tons, which is 4,000 kilogram, and it's accelerate from a rest of 50 seconds over a distance of 460 meter up a hill of 30 degree. Now we need to find a force required to achieve this, and we have a friction of 310 Newton. Now we learned that the sum of force related to the incline is the driving force Q minus the friction, that is 310 Newton, minus the weight of the truck related to the plane, that W sine theta, and all of that equates to the mass times acceleration of the truck, which is the net force. And we know the friction, the magnitude of the friction, and we can find the weight of the truck pulling it down the hill and the net force. First, we need to find the truck's acceleration. We're going to use this formula from the linear motion topic. And when we fill in the formula and we get the acceleration of 0.368 meter per second square. So it's just slowly going up the hill. And we go back to our first formula and fill all that in, and we get our Q, which is 3090 Newton. And that is the driving force of the truck going up a 30 degree hill. Now, what if the truck is going down the incline? Now we have a diesel unit on a train with a mass of 200 megagram and a tractive resistance of 50 Newton per megagram of the train mass, accelerate uniformly from rest to 42 km per hour over 1 kilometer of distance. Now calculate the force required to drive the train down the incline of 1 in 200. Now, first, what variables do we know? We have the mass of 200 megagram, which we have to convert to the standard units. So mega to kilo is a difference of 3 zeros, so we get 200,000 kilogram. And our friction or tractive resistance is given as 50 Newton per megagram. We have 200 megagram, so 50 times 200 megagram is 10,000 newtons of friction. In initial velocity is 0, Final velocity is 42 km per hour, and when divided by 3.6 is 11.67 meter per second. And our distance is 1 kilometer, and our angle is the inverse tan of 1 over 200, which what this means is for every 1 meter vertical height is 200 meter of horizontal length, and that gives us 0.2864 degree of incline. Now, since the unit is going down the incline, the weight actually help it going down. So we add W time sine theta instead of subtracting it like we went uphill. For acceleration, we use this formula, and we get the 0.0681 meter per second square of acceleration, and we just fill in the formula and give us Q of 136,392 Newton. You can convert that to kilonewton if you want. Now, here's a harder one. We got a body mass of 2 megagram pulling up an incline of 27 degree, which is with the horizontal force of 14.25 kilonewton, which has an upward angle of 20 degree with an incline shown by arrow A in the diagram. So we have the coefficient of friction between the plane and the body is 0.25. Now they want us to find the uniform acceleration of the body with the force pulling it forward, and B, the uniform acceleration from rest of the body down the slope if the force is removed. So pretty much the weight of the body, just letting it slide down the slope. And then C, show by calculation that the body will remain at rest if the force pulling it is replaced by another force pushing it, as represented by B. And now we write down our units, our known variables, mass, the force pulling, and our mu, that is 0.25, that mu, the coefficient of friction. So, uniform acceleration of the body. So we have our free body diagram on the right, and we have all the necessary vertical and horizontal forces drawn. Now we're looking at the vertical force, the sum of it equals 0. And here we have our weight of the body minus the vertical pulling force minus the normal force, and all that we get normal force of that much. And remember that formula that we have the sum of horizontal force equal net force. So this bit here, that would be the P cosine 20, and this bit would be the force friction force. So we got the mu times n, and this bit would be the weight of the body pulling it down the hill, and that's equate to mass time acceleration. And from there we solve for acceleration which is 0.67, going up the hill slowly. And second part, it's a uniform acceleration from rest, the body going down the slope if the force pulling is removed. So with no force pulling it, the weight of the body would pull it down the slope. So sum of vertical force equal the weight minus net normal force. That's equal 0. And we solve for normal force there. And here the sum of horizontal force equal mass times acceleration equal the weight pulling it down the hill minus the friction. And we put our normal force in there and solve for acceleration of 2.27 meter per second square going down the hill. In part C, show by calculation that the body will remain at rest if the pulling force is replaced by the pushing force of the same magnitude. So here we remove the pulling force and we place that same magnitude, pushing it at a 20-degree incline instead. So here we still have our vertical force pushing down and horizontal force of the pushing force going along the hill. Now, sum of vertical force. We got our weight here, and we got our force of the pushing force here, the vertical component, and the normal force minus that. So here we added the vertical component since it's going the same direction, and we solve for normal force. There. Now, sum of horizontal force. We put all of our known variable in and solve for A, acceleration by negative 0.553 meter per second square. So same magnitude pushing up, the body will fall down the incline since the upward force is lower than the downward force. So the pushing force of 14.25 kilonewton pushing at that angle isn't enough to pushing the body upward. So it will fall down slowly. So to achieve the equilibrium, we do the same thing. So sum of vertical force, we got the normal force here, but we don't know the pushing force, and we save that one for later. And now the sum of horizontal force, we got our usual, which is that bit there, the horizontal component, minus the friction, minus the weight of the object, of the body. We fill that all in, and we replaced our substitute the normal force with that bit there, which is this here, and we solve for P. The pushing force, it needs to be 15.54 kilonewton or greater to accelerate the body uphill. Now, to keep the body at rest, a force of 15.45 kilonewton is needed, pushing at 20-degree angle as shown to keep it still. Pushing it any more, if you have a greater force, it would accelerate up the hill.